Tonight, we're going to talk about a boundary that exists at the very edge of reality itself, a wall made not of matter or energy, but of time and space. A barrier so absolute that nothing, not even light traveling at its maximum speed for the entire lifetime of the universe, could ever cross it. It's not made of anything physical. You can't touch it, you can't see it, you can't measure it directly, but it's there, separating us from regions of space that might as well exist in a different universe entirely. Scientists call it the cosmic horizon, and it represents something profound about the nature of reality itself. It tells us that the universe has limits, boundaries beyond which we cannot see, cannot travel, cannot even send a signal. And what makes it even more extraordinary is that this boundary is moving. Right now, as you're reading this, galaxies are crossing it. Entire island universes, each containing hundreds of billions of stars, are slipping beyond this edge, disappearing from our observable reality forever. Not because they're being destroyed, not because they're moving through space, but because the fabric of space itself is expanding so rapidly that light from those galaxies can no longer reach us. By the end of tonight, you're going to understand why there are galaxies out there, real galaxies filled with hundreds of billions of stars that we will never see, never visit, and never know anything about, no matter how long we wait or how advanced our technology becomes. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Imagine standing on a beach, looking out at the ocean. There's a clear line where the water meets the sky, a horizon that marks the limit of how far you can see. If you walk forward, that horizon moves with you, always staying the same distance away. No matter how far you travel, you can never actually reach it because it's not a physical place. It's just the consequence of standing on a curved surface with a limited range of vision. The universe has something similar. A cosmic horizon that marks the edge of everything we can possibly observe. But unlike the ocean's horizon, which is just an illusion created by Earth's curvature, the cosmic horizon is real, in a way that's almost impossible to comprehend. It's not just the edge of what we can see, it's the edge of what can possibly affect us, influence us, or ever be known to us in any way. And here's the truly mind-bending part. Right now, at this very moment, galaxies are crossing that horizon. They're slipping over the edge, not into some void or alternate dimension, but into a region of space that is expanding away from us so quickly that light from those galaxies will never reach Earth. Not in a billion years. Not in a trillion years. Never. These galaxies still exist. They're still out there, filled with stars and planets and possibly even life. But as far as we're concerned, as far as anyone in our galaxy or our local group of galaxies is concerned, they might as well not exist at all. They've crossed a boundary beyond which communication, observation, or interaction of any kind becomes fundamentally impossible. To understand this cosmic horizon, we need to talk about something that seems simple on the surface, but becomes increasingly strange the more you think about it: the speed of light. We're used to thinking of the speed of light as the universal speed limit, the fastest anything can possibly travel through space. Light moves at about 186,282 miles per second. In 1 year, traveling at that constant, incredible speed, light covers roughly 5.878 trillion miles. We call that distance a light year, and it's the standard measuring stick for cosmic distances. When we see a galaxy that's 1 million light-years away, we're seeing it as it looked 1 million years ago. The light that's hitting our telescopes right now left that galaxy 1 million years in the past. This creates a strange situation where looking out into space means looking back in time. The farther we peer into the cosmos, the further into the past we see. But here's where things get weird. The universe is expanding. Not just getting bigger in the sense that things are moving apart within space, but space itself is stretching, creating more distance between distant objects. This expansion was discovered in the 1920s by Edwin Hubble, who noticed that almost every galaxy he observed was moving away from us. More importantly, he noticed a pattern. The farther away a galaxy was, the faster it was receding. Galaxies twice as far away were moving away twice as fast. This relationship, now called Hubble's law, told us something profound about the nature of the universe. It's not that we're at the center of some cosmic explosion with everything flying away from us. It's that space itself is expanding everywhere, all at once. Imagine drawing dots on a balloon and then inflating it. As the rubber stretches, every dot moves away from every other dot. Dots that are close together separate slowly. Dots that are far apart separate quickly. None of the dots are moving through the rubber. They're just being carried along as the rubber itself expands. That's what's happening with galaxies in our universe. They're embedded in the fabric of space, and as space expands, they get carried along with it. Now, here's the critical insight. Because space itself is expanding, and because the rate of expansion depends on distance, there's a point beyond which space is expanding so quickly that light from those distant regions can never reach us. Think about it this way. Light is traveling toward us at 186,282 miles per second. But the space between us and that distant galaxy is also expanding, creating more distance that the light has to cross. If the space is expanding slowly, the light will eventually make it. It might take billions of years, but it will get here. But if the space is expanding faster than the light can travel through it, the light never makes any progress toward us. It's like trying to run up a treadmill that's moving faster than you can run. No matter how hard you try, you'll never get anywhere. You're moving. You're making an effort, but the ground beneath you is moving backward faster than you're moving forward. For light trying to reach us from the most distant parts of the universe, space is the treadmill, and it's moving too fast. This creates a sphere around us, centered on Earth, beyond which we cannot see. Not because there's nothing there, but because the light from those regions is fighting a losing battle against the expansion of space itself. This sphere is called the cosmic horizon, and it defines the observable universe. Everything inside the cosmic horizon is, at least in principle, observable. Everything outside it is not. And here's where it gets even stranger. The cosmic horizon isn't sitting still. It's changing. But not in the way you might expect. You might think that as time passes and light has more time to travel, the cosmic horizon would expand, allowing us to see more and more of the universe. And for much of the history of the universe, that's exactly what happened. In the early universe, the cosmic horizon was much smaller than it is today. As time passed, light from more distant regions had time to reach us, and the observable universe grew. But something changed about 5 billion years ago. The expansion of the universe started accelerating. We don't fully understand why this is happening. We attribute it to something we call dark energy, a mysterious force that seems to be pushing space apart with ever-increasing strength. But we don't know what dark energy actually is. We just know that it exists because we can see its effects. And one of those effects is that the cosmic horizon is now shrinking in a certain sense. Not shrinking in terms of physical size, the observable universe is still about 93 billion light-years across, but shrinking in terms of the number of galaxies it contains. As the expansion accelerates, galaxies that are currently inside our cosmic horizon are being pushed beyond it. They're crossing the boundary from observable to unobservable. Right now, as you're watching this, there are galaxies slipping over the edge. Their light, which has been traveling toward us for billions of years, will never complete the journey. Space is expanding too quickly now. The light is losing the race. Let me give you some numbers to make this more concrete. The current best estimate puts the edge of our cosmic horizon at about 46.5 billion light-years away. That might seem confusing at first. If the universe is only 13.8 billion years old, how can we see objects that are 46.5 billion light-years away? Shouldn't the farthest thing we can see be 13.8 billion light-years away, since that's how long light has had to travel? The answer lies in the expansion of space. When we see a galaxy that's 46.5 billion light-years away, we're not seeing it as it is now. We're seeing it as it was 13.8 billion years ago, shortly after the Big Bang. But during the time that light has been traveling toward us, space has been expanding, stretching the distance between us and that galaxy. So even though the light has only been traveling for 13.8 billion years, the galaxy it came from is now 46.5 billion light-years away. And here's the thing. That galaxy, the one we're seeing as it was 13.8 billion years ago, has already crossed our cosmic horizon. The light we're receiving from it now is the last light that will ever reach us from that galaxy. Any light it emits from this point forward will never make it to Earth. It's gone, slipped beyond the edge of the observable universe into a region of space that is expanding away from us faster than light can travel. Over time, more and more galaxies will follow. Currently, there are about 2 trillion galaxies in the observable universe. That's 2 trillion island universes, each containing hundreds of billions of stars. But this number is decreasing. Every moment, galaxies are crossing the cosmic horizon, disappearing from view forever. In the far future, billions of years from now, the night sky will look very different than it does today. The Andromeda Galaxy, our nearest large galactic neighbor, will have merged with the Milky Way, creating a single enormous elliptical galaxy. But beyond our local group of galaxies, the universe will appear empty. All those distant galaxies, all those trillions of island universes, will have receded beyond the cosmic horizon. Their light will no longer reach us. An astronomer living in that far future would look out at the universe and see almost nothing beyond their own galaxy. They would have no way of knowing that the universe is expanding, because there would be nothing nearby to observe expanding. They would have no way of knowing about the Big Bang, because the cosmic microwave background radiation, the afterglow of the Big Bang, would have redshifted so much that it would be undetectable. They would live in a universe that, as far as they could tell, consisted of a single galaxy surrounded by empty space. They would have no way of knowing that they were living in an expanding universe filled with trillions of galaxies, because all the evidence would have crossed the cosmic horizon. Think about what that means. The era in which we live, right now, is a special time in cosmic history. We can still see the cosmic microwave background. We can still observe distant galaxies and measure the expansion of the universe. We can still piece together the history of the cosmos, from the Big Bang to the present day. But this won't last forever. The universe is actively erasing its own history. With each passing moment, more evidence of the Big Bang, more distant galaxies, more cosmic structure slips beyond the horizon and is lost to us forever. Future civilizations, if they exist, will have a much harder time understanding the universe than we do, simply because they'll have access to less information. The evidence will have literally moved beyond their reach. Now, let's talk about what the cosmic horizon means for the possibility of communication or contact with distant civilizations. Science fiction is filled with stories of vast galactic empires, civilizations spanning multiple galaxies, faster-than-light travel connecting distant corners of the universe. But the cosmic horizon puts a hard limit on all of this. Any civilization that exists beyond our cosmic horizon is not just unreachable, they're unknowable. We can never communicate with them, never visit them, never even be aware of their existence, and they can never be aware of ours. It's not a technological limitation. It's a fundamental property of the universe itself. No matter how advanced we become, no matter what technologies we develop, we can never cross the cosmic horizon. It's an absolute boundary, as uncrossable as the event horizon of a black hole. In fact, the cosmic horizon has a lot in common with a black hole's event horizon. Both represent boundaries beyond which information cannot travel. For a black hole, nothing inside the event horizon can send information to the outside universe. For the cosmic horizon, nothing beyond it can send information to us. Both boundaries are created by extreme space-time curvature or expansion. Both are absolute and uncrossable. But there's a key difference. With a black hole's event horizon, there's at least theoretically a direction you could travel to reach it. You could, if you were willing to accept that you could never return, cross a black hole's event horizon. But the cosmic horizon is different. You can't travel to it because it's not a place. It's a consequence of expansion. If you started traveling toward the cosmic horizon right now, moving at the speed of light, you would never reach it. In fact, you wouldn't even get close. The space between you and the horizon would expand faster than you could cross it. The horizon would recede ahead of you, always staying the same distance away, just like the horizon on the ocean stays the same distance away no matter how far you walk. This has profound implications for the future of civilization. Our descendants, no matter how advanced they become, will be confined to a region of space defined by the cosmic horizon, and that region is shrinking. Currently, the observable universe contains about 2 trillion galaxies, but our gravitational influence only extends to our local group of galaxies. The local group consists of the Milky Way, Andromeda, and about 50 smaller galaxies. Together, they're gravitationally bound to each other, meaning they won't be separated by the expansion of space. In fact, as I mentioned earlier, the Milky Way and Andromeda are actually moving toward each other and will eventually merge. But beyond the local group, everything is moving away from us. The expansion of space is overcoming the gravitational attraction between us and those distant galaxies. Given enough time, every galaxy outside our local group will cross the cosmic horizon and disappear from view. Our descendants will be confined to the local group. That might sound like a lot of space, and it is. The local group contains about 3 trillion solar masses worth of material. That's enough stars and planets to keep a civilization busy for a very long time. But it's a tiny fraction of the total universe. Out of 2 trillion galaxies in the observable universe, we'll eventually have access to about 50. That's 0.000025% of the observable universe. The rest will be forever beyond our reach. Not because we lack the technology to get there, but because the universe itself won't allow it. Now, you might be wondering, is there anything beyond the cosmic horizon? The answer is almost certainly yes. The cosmic horizon marks the edge of the observable universe, not the edge of the universe itself. In fact, there's good reason to believe that the universe is infinite, or at least vastly larger than the observable portion. The cosmic microwave background radiation, the afterglow of the Big Bang, shows a pattern of tiny temperature fluctuations. These fluctuations tell us about the density variations in the early universe, the seeds that would eventually grow into galaxies and galaxy clusters. By studying these fluctuations, we can determine the curvature of space. Is the universe curved, like the surface of a sphere? Or is it flat, like an infinite plane? Or is it curved in the opposite way, like a saddle? The measurements we've made indicate that the universe is flat, or at least very close to flat. So close that we can't detect any curvature. A flat universe that's finite would have to have some kind of edge or boundary, and we see no evidence for that. The most straightforward interpretation is that the universe is infinite, extending forever in all directions. If that's true, then beyond our cosmic horizon, there are infinitely many more galaxies, infinitely more stars, infinitely more planets. There could be an infinite number of civilizations out there, living in regions of space that are forever separated from us by the expansion of space-time. Some of those regions might be very similar to ours. In an infinite universe, given enough space, every possible configuration of matter will occur, not just once, but infinitely many times. There could be an infinite number of Earths out there, with an infinite number of people watching this right now, in galaxies beyond our cosmic horizon. Of course, we can never verify this. By definition, anything beyond the cosmic horizon is unobservable. We can theorize about it, we can make mathematical models, but we can never actually see it or interact with it in any way. It exists in a realm that is, for all practical purposes, completely separate from our own. This raises some interesting philosophical questions. If something exists but can never be observed or interacted with in any way, does it really exist in any meaningful sense? Most physicists would say yes. The laws of physics don't stop at our cosmic horizon. Space continues to exist beyond it, and presumably, it's filled with galaxies and stars and planets, just like the space inside our horizon. But from a practical standpoint, from the perspective of anyone living in our universe, it might as well not exist. It can never affect us, and we can never affect it. It's completely cut off from our reality. Let me tell you about one more strange consequence of the cosmic horizon. It's related to something called Hubble's law, which I mentioned earlier. Hubble's law states that the recession velocity of a galaxy is proportional to its distance. Galaxies twice as far away are receding twice as fast. We can express this as a simple equation. Velocity equals distance times the Hubble constant. The Hubble constant is a number that describes the rate of expansion of the universe. Currently, it's about 46 miles per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of distance, the recession velocity increases by about 46 miles per second. Now, let's do some math. If we keep going to greater and greater distances, eventually we'll reach a distance where the recession velocity equals the speed of light. Divide the speed of light, 186,282 miles per second, by the Hubble constant, 46 miles per second per megaparsec, and you get about 4,046 megaparsecs. Convert that to light years, and you get about 13.2 billion light years. This is called the Hubble distance, and it has special significance. At the Hubble distance, objects are receding from us at exactly the speed of light. Beyond the Hubble distance, objects are receding faster than light. Now, you might be thinking, wait a minute, didn't you just say that nothing can move faster than light? And you'd be right. Nothing can move faster than light through space, but space itself can expand at any rate. There's no speed limit on the expansion of space. So galaxies beyond the Hubble distance aren't actually moving faster than light through space. They're sitting relatively still in their own patch of space. It's the space between us and them that's expanding so quickly that the distance is increasing faster than light could travel across it. This is what creates the cosmic horizon. The cosmic horizon is located at a distance somewhat beyond the Hubble distance, roughly 46.5 billion light-years away. Anything beyond that distance is receding so quickly that light from it can never reach us. But here's the strange part. The Hubble distance itself is inside the cosmic horizon. That means there are galaxies that are currently receding from us faster than the speed of light, but we can still see them. How is that possible? The answer has to do with the history of the expansion. In the past, the universe was smaller, and the expansion rate was different. Light that left those galaxies billions of years ago started out in a region where space was expanding slower than it is now. At that time, the light was making progress toward us. As space expanded and the expansion accelerated, the light found itself in regions where space was expanding faster and faster. Eventually, it crossed into regions where space was expanding faster than the speed of light. But by that point, the light had already made enough progress that it could eventually reach us. It's like a salmon swimming upstream. If the salmon starts in a slow part of the river and swims hard, it can make progress upstream. Even if it then enters a faster part of the river where the water is moving faster than the salmon can swim, the salmon might still make it to its destination because of the progress it already made in the slower section. But a salmon that starts in the fast part of the river will never make it. It will be swept downstream no matter how hard it swims. Light works the same way. Light that started its journey in the early universe, when expansion was slower, can still reach us, even though it's currently in regions where space is expanding faster than light. But light emitted now from those same galaxies will never reach us. The expansion is too fast. Those galaxies have crossed the Hubble distance and are on their way to crossing the cosmic horizon. In fact, there are galaxies we can see right now that have already crossed the cosmic horizon. We're seeing them as they were in the distant past, and the light we're receiving now is the last light from them that will ever reach Earth. It's already been traveling for more than 13 billion years, and it's just now arriving. But any light emitted from those galaxies more recently has no chance of ever reaching us. The expansion is too fast. Those photons are fighting a losing battle, traveling through a universe that's expanding faster than they can cross it. Think about that for a moment. Right now, at this very instant, there are galaxies in the night sky that no longer exist as far as we're concerned. We're seeing their ancient light that left those galaxies billions of years ago. But the galaxies themselves, as they exist right now, are beyond the cosmic horizon. We can never know what they look like today. We can never receive any information about their current state. We can only see them frozen in time, as they were in the distant past, sending us the last messages they will ever send before slipping forever beyond the edge of the observable universe. This creates a strange kind of cosmic archaeology. When we look at the most distant galaxies, we're not just looking at distant objects, we're looking at a time capsule, a snapshot of the universe as it was more than 13 billion years ago. Those galaxies have evolved since then. They've formed new stars. Some of those stars have gone supernova, planets may have formed around them, life may have arisen, but we'll never know. All we have is this ancient light, carrying information about what those galaxies looked like in their youth, nothing more. And soon, even that will be gone. As those galaxies continue to recede, their light will become more and more red-shifted, stretched to longer and longer wavelengths by the expansion of space. Eventually, the light will be shifted so far into the infrared, and then the microwave, and then the radio spectrum, that it will be undetectable. The galaxies will fade from view, not because their light stopped reaching us, but because the light became so stretched by expansion that it effectively disappeared. Now, let's talk about what all of this means for the fate of the universe. The cosmic horizon is not just a boundary in space. It's also a window into the future. By studying how the cosmic horizon changes over time, we can learn about the ultimate fate of everything. Currently, the expansion of the universe is accelerating. This acceleration is driven by dark energy, which appears to be a property of space itself. The more space there is, the more dark energy there is, and the faster the expansion accelerates. If this continues, and all our evidence suggests it will, the expansion will keep accelerating forever. The cosmic horizon will keep shrinking in terms of the number of galaxies it contains. Eventually, billions of years from now, Every galaxy outside our local group will have crossed the horizon. The observable universe will contain just our local group and nothing else. But even that won't be the end. Stars have finite lifetimes. They burn through their fuel and die. The most massive stars live for just a few million years. Medium-sized stars like our Sun live for about 10 billion years. The smallest stars, tiny red dwarfs, can live for trillions of years, but eventually, even they will run out of fuel. In about 100 trillion years, the last stars in the universe will burn out. The universe will enter what's called the degenerate era, a time when the only objects left are dead, stellar remnants like white dwarfs, neutron stars, and black holes. These objects will continue to exist, orbiting each other, slowly radiating away their energy, but there will be no more star formation, no more light, no more warmth. The universe will be dark and cold. And even this isn't the end. Over unimaginably long timescales, even these dead remnants will decay. Protons, the building blocks of atoms, are not actually stable on very long timescales. They decay, with a half-life estimated at about 10 to the power of 34 years. That's a 1 followed by 34 zeros. It's so long that no proton in the universe has decayed yet. Not in the 13.8 billion years since the Big Bang, but given enough time, they all will. In about 10 to the power of 40 years, all the matter in the universe will have decayed into photons and leptons. Even black holes won't survive forever. Stephen Hawking showed that black holes actually evaporate, slowly radiating away their mass through a process called Hawking radiation. The rate is incredibly slow. A solar mass black hole would take about 10 to the power of 67 years to evaporate. A supermassive black hole, weighing billions of solar masses, would take vastly longer, but eventually every black hole will evaporate. And then the universe will contain nothing but photons and leptons spread out across an ever-expanding space, growing more and more dilute. This is called the heat death of the universe. It's a state of maximum entropy, where no more useful work can be done, no more interesting structures can form. The universe will have reached thermodynamic equilibrium, and it will remain in that state forever. The expansion will continue, space will keep growing, but nothing will ever happen again. No stars, no planets, no life, no thought, no consciousness, just empty space, growing larger and emptier for eternity. This is, according to our current understanding, the ultimate fate of the universe. It's not a pleasant picture, but it's important to remember that we're talking about timescales so vast that they're almost meaningless. 10 to the power of 40 years. 10 to the power of 67 years. These numbers are so large that there's no way to truly comprehend them. The entire history of the universe so far, all 13.8 billion years, is less than a trillionth of a trillionth of a trillionth of a percent of these timescales. We're living in the very, very, very early universe, in a special time when stars are still shining, galaxies are still forming, and complex structures like planets and life can exist. This won't last forever, but it will last for a very, very long time by human standards. Let me bring this back to something more immediate. What does the cosmic horizon mean for us, right now, living on Earth in the early 21st century? In practical terms, it means very little. The cosmic horizon is so far away that it has no direct impact on our daily lives. We can't travel anywhere near it. We can't communicate with anything beyond it. We'll never have any physical interaction with it. But in a deeper sense, it changes everything. The cosmic horizon tells us that the universe, as vast and mysterious as it is, has limits. There are fundamental boundaries beyond which we cannot go, questions we cannot answer, regions of space we can never explore. This is humbling. It reminds us that for all our intelligence and technology, we are still bound by the laws of physics. We are still limited creatures, living in a universe far larger and stranger than we can fully comprehend. But it's also liberating, because if there are regions of the universe we can never explore, then we might as well focus on what we can explore. The observable universe is still unimaginably vast. It contains 2 trillion galaxies, each with billions or trillions of stars. Even if we could never leave our own galaxy, the Milky Way alone contains hundreds of billions of stars and potentially trillions of planets. That's more than enough to keep humanity busy for millions or billions of years. And who knows what we might discover along the way. The cosmic horizon also raises profound questions about the nature of reality. If there are regions of the universe that are forever beyond our reach, does it even make sense to talk about them as part of our universe? Some philosophers would say no. If something can never be observed or interacted with in any way, it's not part of our reality. It exists in some abstract mathematical sense, but not in any practical, meaningful sense. Others would disagree. They would argue that just because we can't see something doesn't mean it doesn't exist. The laws of physics extend beyond our cosmic horizon. Space continues to exist out there, filled with galaxies and stars and planets, even if we can never see them. This is ultimately a question that science cannot answer. We can describe what the cosmic horizon is. We can explain why it exists. We can predict what will happen to it in the future. But whether regions beyond it are real, in some deeper sense, is a philosophical question, not a scientific one. There's one more aspect of the cosmic horizon that I want to discuss, because it touches on something truly profound about the nature of scientific knowledge. The cosmic horizon represents a fundamental limit to what we can know about the universe. No matter how clever we are, no matter how sophisticated our instruments become, there are things we will never be able to observe or measure or verify. This is different from the limitations we face in other areas of science. If we want to know what's at the bottom of the ocean, we can build submarines that can take us there. If we want to know what atoms are made of, we can build particle accelerators to smash them apart and see what's inside. These are technological challenges, not fundamental limits. Given enough time and resources, we can overcome them. But the cosmic horizon is different. It's not a technological limitation. It's a fundamental property of the universe itself. No technology, no matter how advanced, can allow us to see beyond the cosmic horizon. The laws of physics themselves prevent it. This means that there are questions about the universe that we can never answer through observation. We can theorize about what lies beyond the cosmic horizon. We can build mathematical models. We can make educated guesses. But we can never verify those theories through direct observation. This is deeply troubling to some scientists. Science is supposed to be about testing theories against observations, making predictions and then checking whether those predictions come true. But if we're making claims about regions of the universe that are fundamentally unobservable, how can we call that science? Some would argue that it's not science at all, but rather a kind of mathematical philosophy. Interesting and intellectually stimulating, perhaps, but not subject to the usual rules of scientific verification. Others would argue that it's still science, because the theories we develop are constrained by what we can observe. We can't see beyond the cosmic horizon, but we can see the cosmic microwave background. We can measure the expansion rate of the universe. We can observe the distribution of galaxies. All of this gives us information about the overall structure and history of the universe, which we can then extrapolate to regions we can't directly observe. This debate goes to the heart of what we mean by science and scientific knowledge. Is science just about describing what we can observe? Or is it about building theoretical frameworks that explain observations and make predictions? Even if some of those predictions can never be directly tested. These are not easy questions, and I don't pretend to have definitive answers. But they're worth thinking about, because they remind us that the cosmic horizon is not just a physical boundary, it's also an epistemological boundary, a limit to what we can know. And grappling with that limit forces us to think carefully about the nature of knowledge itself. Let me tell you about one final implication of the cosmic horizon, because it's both beautiful and melancholy. The cosmic horizon means that we are living in a special time. Right now, in the early 21st century, about 13.8 billion years after the Big Bang, we can still see most of the observable universe. We can still see distant galaxies. We can still detect the cosmic microwave background. We can still piece together the history of the cosmos. But this window is closing. Every moment, more galaxies cross the cosmic horizon and disappear from view. Every moment, the cosmic microwave background becomes more redshifted and harder to detect. Every moment, the evidence of the Big Bang becomes fainter. In the far future, billions of years from now, astronomers living in our local group will look out at the universe and see almost nothing. The cosmic microwave background will be undetectable. Distant galaxies will have vanished. All the evidence that the universe began in a hot, dense state and has been expanding ever since will be gone. Those future astronomers will have a much harder time figuring out the true nature of the universe, simply because they'll have access to less information. In a very real sense, we are privileged. We live at a time when the universe is still revealing its secrets, when the evidence of the Big Bang is still accessible, when we can still observe distant galaxies and measure the expansion of space. This privilege won't last forever. The universe is slowly erasing its own history, and we are among the last generations who will have access to the full story. This creates a kind of cosmic responsibility. We have the opportunity, right now, to learn about the universe in ways that future civilizations may not be able to. We can observe things that will become unobservable. We can measure things that will become unmeasurable. We can piece together a history that will become inaccessible. In a sense, we are living in a golden age of cosmology. We have the technology to observe the universe across the entire electromagnetic spectrum, from radio waves to gamma rays. We have telescopes in space that can see farther and more clearly than ever before. We have sophisticated mathematical models that can simulate the evolution of the universe from the Big Bang to the present day. And we're using these tools to answer some of the most profound questions humans have ever asked. Where did we come from? How did the universe begin? What is it made of? How will it end? These are not small questions. They're the biggest questions we can possibly ask. And we're living at a time when, for the first time in human history, we can actually answer them. Not completely, not perfectly, but well enough to sketch out the broad outline of cosmic history. We know that the universe began about 13.8 billion years ago in an event we call the Big Bang. We know that it's been expanding ever since, and that the expansion is accelerating. We know that it's made mostly of dark matter and dark energy, mysterious substances we don't fully understand, but whose existence we can infer from their gravitational effects. We know that stars and galaxies formed from tiny density fluctuations in the early universe, fluctuations that we can still see imprinted on the cosmic microwave background. We know that our own existence, everything we see and touch and experience, is made from elements created in the hearts of stars that lived and died billions of years ago. We know all of this because we live at a time when the evidence is still accessible. Future civilizations may not have that luxury. They may live in a universe where the cosmic horizon has shrunk so much that all the distant galaxies have disappeared, where the cosmic microwave background has redshifted into oblivion, where the evidence of the Big Bang has faded away. They may look out at the universe and see only their own galaxy, surrounded by empty space, with no way of knowing that they're living in an expanding universe that began in a hot, dense state billions of years ago. This is both sobering and inspiring. Sobering because it reminds us that our window of opportunity is limited. The universe won't wait for us. Inspiring because it emphasizes the importance of what we're doing right now. Every observation we make, every measurement we take, every piece of data we collect is a gift to the future. It's information that may not be accessible to later generations. It's a piece of the puzzle that helps us understand where we came from and where we're going. And in a universe that is constantly changing, constantly evolving, constantly erasing its own past, that's no small thing. So, what have we learned tonight? We've learned that the universe has a horizon, a boundary beyond which we cannot see. We've learned that this horizon is created by the expansion of space, which is stretching the universe and carrying distant galaxies away from us faster than light can travel. We've learned that the cosmic horizon is not fixed, but is changing over time, with more and more galaxies crossing it and disappearing from view. We've learned that the cosmic horizon puts fundamental limits on what we can know and where we can go, confining us forever to a small region of space defined by the expansion rate of the universe. We've learned that there are almost certainly galaxies beyond the cosmic horizon, perhaps infinitely many of them, that we can never see or communicate with or even know about. We've learned that we are living in a special time, a golden age of cosmology, when the evidence of the Big Bang is still accessible and we can still observe distant galaxies and piece together the history of the cosmos. And we've learned that this privilege won't last forever, that the universe is slowly erasing its own history, and that future generations may not have access to the information we have now. The cosmic horizon is a wall at the edge of everything, but it's not a wall made of brick or stone. It's a wall made of space-time itself, a boundary beyond which the very fabric of the universe forbids us to see or travel or communicate. It's absolute, uncrossable, eternal. And it's expanding, growing larger and emptier, swallowing more and more of the universe with each passing moment. This is the reality we live in. A universe with limits, with boundaries, with regions we can never explore and questions we can never answer. It's humbling and awe-inspiring in equal measure. But here's the thing, even with these limits, even with the cosmic horizon cutting us off from most of the universe, what remains is still almost incomprehensibly vast. 2 trillion galaxies, each with hundreds of billions of stars, trillions upon trillions of planets, some of which may harbor life, billions of years of cosmic history, stretching from the Big Bang to the present day and beyond. Countless mysteries still to unravel, phenomena still to discover, questions still to answer. The cosmic horizon may mark the edge of the observable universe, but that's still an awful lot of universe to explore. And we're just getting started. We've only been doing serious astronomy for a few hundred years. We've only had space telescopes for a few decades. We've only been able to detect gravitational waves for less than a decade. Imagine what we might discover in the next 100 years, or the next 1,000, or the next million. Imagine what technologies we might develop, what insights we might gain, what questions we might answer. The cosmic horizon may be a wall at the edge of everything, but it's a wall we're only just beginning to understand. And understanding it, mapping it, studying how it changes over time, these efforts are teaching us profound truths about the nature of reality itself. So yes, there are galaxies we'll never see, civilizations we'll never meet, regions of space we'll never explore. But there are also galaxies we can see, questions we can answer, discoveries we can make. And in a universe as vast and strange and wonderful as ours, that's more than enough. The cosmic horizon is a boundary, a limit, a wall at the edge of everything. but it's also a reminder of how far we've come. A few hundred years ago, we didn't even know that other galaxies existed. We thought the Milky Way was the entire universe. Now we know about 2 trillion galaxies spread across 93 billion light-years of space. We know about the Big Bang, dark matter, dark energy, the expansion of the universe. We know about the cosmic horizon itself, this invisible boundary that marks the limit of the knowable cosmos. That's an extraordinary achievement. And it's an achievement made possible by generations of astronomers and physicists and mathematicians, each building on the work of those who came before. From Galileo pointing his telescope at the sky, to Hubble discovering the expansion of the universe, to modern cosmologists mapping the cosmic microwave background and detecting gravitational waves. Each discovery has added another piece to the puzzle, bringing us closer to understanding the true nature of reality. The cosmic horizon is part of that puzzle. It's a piece that tells us about the limits of the observable universe, the fate of distant galaxies, the ultimate destiny of everything. It's a sobering piece, because it reminds us that some questions may never be answered, some regions may never be explored. But it's also an inspiring piece, because it shows us how much we've learned, how far we've come, and how much there still is to discover. Now I want to take you on a more detailed journey through the history of how we discovered the cosmic horizon. Because understanding how we came to know about this boundary is almost as fascinating as the boundary itself. The story begins, as so many stories in modern cosmology do, with Albert Einstein. In 1915, Einstein published his general theory of relativity, which completely revolutionized our understanding of gravity and space-time. According to general relativity, massive objects don't pull on each other through some mysterious force acting at a distance. Instead, they curve the fabric of space-time itself, and other objects move along the curves created by that curvature. It's a beautiful and elegant theory, and it made predictions that matched observations far better than Newton's older theory of gravity. But Einstein's equations had an interesting property. They describe not just how individual objects move through space-time, but how space-time itself evolves. In other words, Einstein's equations could describe the entire universe. Einstein was curious about this. What did his equations say about the overall structure and evolution of the cosmos? So he applied his equations to the universe as a whole, making some simplifying assumptions. He assumed that the universe was homogeneous, meaning it looks roughly the same everywhere. He assumed it was isotropic, meaning it looks roughly the same in all directions. And he assumed it was static, neither expanding nor contracting, just sitting there unchanging for all eternity. That last assumption seemed perfectly reasonable in 1917. Everyone believed the universe was static. There was no evidence to suggest otherwise. But when Einstein solved his equations with these assumptions, he got a disturbing result. The equations said that a static universe was impossible. Gravity would cause it to collapse in on itself. Einstein was troubled by this. He was so convinced that the universe must be static that he modified his equations, adding a new term he called the cosmological constant. This term represented a kind of repulsive force that could counteract gravity and keep the universe from collapsing. With this modification, Einstein could get a static universe from his equations. Problem solved, or so he thought. But then, in 1929, Edwin Hubble made a discovery that changed everything. Hubble had been studying distant galaxies using the 100-inch telescope at Mount Wilson Observatory in California. He measured the distances to these galaxies using variable stars called Cepheids, which pulse with a brightness that depends on their intrinsic luminosity. By measuring how bright these stars appeared and comparing that to how bright they actually were, Hubble could calculate how far away they were. He also measured the velocities of these galaxies by looking at their spectra, the rainbow of colors produced when you split their light with a prism. If a galaxy was moving away from us, its light would be shifted toward the red end of the spectrum. If it was moving toward us, its light would be shifted toward the blue end. This is called the Doppler effect, the same effect that makes the pitch of a siren change as an ambulance drives past you. What Hubble found was stunning. Almost every galaxy he looked at was redshifted, meaning it was moving away from us. And the farther away a galaxy was, the faster it was receding. This relationship was linear, double the distance, double the recession velocity. This was not what you'd expect from a static universe. It was what you'd expect from an expanding universe. If space itself was expanding, carrying galaxies along with it, then distant galaxies would naturally be receding faster than nearby ones. Hubble's discovery meant that Einstein's cosmological constant was unnecessary. The universe wasn't static after all. It was expanding. Einstein later called the cosmological constant his greatest blunder. But here's the ironic twist. Decades later, in 1998, astronomers discovered that the expansion of the universe is actually accelerating. This acceleration requires something very much like Einstein's cosmological constant. We now call it dark energy, and it appears to be a property of space itself, causing the expansion to speed up over time. So Einstein's blunder turned out to be prophetic. The cosmological constant, in the form of dark energy, is real after all. It just doesn't work the way Einstein originally thought it did. Instead of preventing the universe from collapsing, it's causing it to expand faster and faster. And it's this accelerating expansion, driven by dark energy, that creates the cosmic horizon. Let me explain in more detail how the cosmic horizon actually works, because the physics is subtle and easy to misunderstand. When we say that a galaxy is beyond the cosmic horizon, we don't mean that it's simply very far away. We mean something more fundamental. We mean that light from that galaxy, emitted now, will never reach us, no matter how long we wait. This is not because the light gets absorbed or scattered along the way. It's because the space between us and that galaxy is expanding so fast that the light can't make any headway toward us. Imagine you're standing on a moving sidewalk at an airport. The sidewalk is moving at 3 miles per hour, and you're walking on it at 4 miles per hour. If you walk in the same direction as the sidewalk is moving, you'll move at 7 miles per hour relative to the ground. If you walk against the direction of the sidewalk, you'll move at 1 mile per hour relative to the ground. You're still making progress, just slowly. Now imagine that the sidewalk speeds up to 5 miles per hour. If you're still walking at 4 miles per hour against its motion, you're no longer making any progress toward your destination. In fact, you're moving backward at 1 mile per hour, even though you're walking forward. That's what's happening with light from distant galaxies. The light is traveling toward us at the speed of light, about 186,282 miles per second. But the space between us and those galaxies is expanding. If the space is expanding slowly, the light makes progress toward us. If the space is expanding at exactly the speed of light, the light stays in the same place, neither getting closer nor farther away. If the space is expanding faster than the speed of light, the light is actually getting farther away from us, even though it's traveling toward us at its maximum possible speed. This last case is what defines the cosmic horizon. Galaxies beyond the cosmic horizon are receding so fast that space between us and them is expanding faster than light can cross it. Light from those galaxies will never reach us. But here's where it gets really interesting. The cosmic horizon is not at a fixed distance. It's constantly changing because the expansion rate of the universe is changing. In the early universe, the expansion was slowing down. Gravity was pulling on all the matter in the universe, trying to slow the expansion. During this period, the cosmic horizon was getting farther away. More and more galaxies were coming into view as their light finally had time to reach us. But about 5 billion years ago, something changed. The expansion stopped slowing down and started speeding up. Dark energy, which had always been there but was less important when the universe was smaller and denser, became the dominant force. And dark energy doesn't slow down the expansion, it accelerates it. Since then, the cosmic horizon has been doing something strange. In terms of physical distance, it's still getting farther away. But in terms of the number of galaxies it contains, it's shrinking. Galaxies that were inside the cosmic horizon 5 billion years ago are now outside it. Their light, which was making progress toward us, is now fighting a losing battle. It's still traveling toward us, but space is expanding so fast that it's actually getting farther away. These galaxies have crossed the cosmic horizon, not by moving through space, but by the expansion of space, accelerating past a critical threshold. And once a galaxy crosses the cosmic horizon, it can never come back. The expansion will only continue to accelerate, carrying that galaxy farther and farther away, until it's so far that its light is redshifted to the point of being undetectable. Let me give you a concrete example to make this more tangible. There's a galaxy called GNZ 11. It's one of the most distant galaxies ever observed, located about 32 billion light-years away. Now, you might notice that this distance is less than the 46.5 billion light-years to the cosmic horizon. So GNZ 11 is still inside the cosmic horizon, right? Yes, but just barely. And it won't be for long. The light we're seeing from GNZ 11 was emitted when the universe was only about 400 million years old, just 3% of its current age. That light has been traveling toward us for more than 13 billion years. During that time, the universe has expanded, stretching the distance between us and GNZ 11 from about 2.6 billion light-years, when the light was emitted, to 32 billion light-years today. The light has been making progress toward us, but it's been fighting against the expansion of space the whole way, and it's winning, but only barely. Any light emitted by GNZ 11 more recently has less time to reach us before the expansion carries it beyond the horizon. At some point, probably within the next few billion years, GNZ 11 will emit light that will never reach us. That light will cross over the threshold, into the region where space is expanding faster than the light can travel through it. And from that point on, GNZ 11 will begin to fade from view. The light we're receiving now will become more and more redshifted. The galaxy will appear dimmer and dimmer. Eventually, it will disappear completely, not because it stopped existing, but because its light can no longer reach us. This is happening to galaxies all over the universe. Right now, at this moment, there are countless galaxies crossing the cosmic horizon. Some of them are galaxies we've observed, galaxies we've studied, galaxies we've given names and catalog numbers to. Others are galaxies we've never seen, galaxies too faint or too distant for our current telescopes to detect. But whether we've seen them or not, they're all crossing the same boundary. They're all slipping beyond the edge of the observable universe. And once they cross that boundary, they're gone forever. Now, let's talk about what this means for the structure of the observable universe. The observable universe is not a fixed thing. It's constantly changing, growing in some ways and shrinking in others. In terms of volume, the observable universe is always growing. As time passes, light from more distant regions has time to reach us. The cosmic horizon is currently about 46.5 billion light-years away, and it's getting farther. In another billion years, it might be 48 billion light-years away. In 10 billion years, it might be 60 billion light-years away. So in that sense, we're able to see more and more of the universe as time goes on. But in terms of content, the observable universe is shrinking. The number of galaxies it contains is decreasing. Galaxies are crossing the horizon, and disappearing from view faster than new regions are coming into view. This is because the expansion is accelerating. In a universe with no acceleration, the cosmic horizon would just keep expanding, and we'd keep seeing more and more galaxies. But in an accelerating universe, galaxies that are currently visible will eventually be pushed beyond the horizon. And the acceleration is getting stronger, not weaker. Dark energy is becoming more and more dominant as the universe expands. This means that the rate at which galaxies are crossing the horizon is increasing. We're losing galaxies faster now than we were 1 billion years ago. And we'll lose them even faster 1 billion years from now. Eventually, in the far future, the only galaxies that will be visible will be the ones in our local group. The Milky Way, Andromeda, and about 50 smaller galaxies. Everything else will have crossed the cosmic horizon. The observable universe will contain just our local group and nothing else. No distant galaxies, no galaxy clusters, no cosmic web of large-scale structure, just our little island of galaxies, surrounded by empty space. This raises an interesting question. What happens to the concept of the observable universe when there's almost nothing to observe? In a sense, the observable universe becomes almost meaningless. If all you can see is your own local group of galaxies, you might as well just call that the universe and be done with it. You'd have no way of knowing that there's anything beyond it. No way of knowing that the universe is expanding. No way of knowing about the Big Bang. All the evidence would be gone, erased by the expansion of space. This brings me to one of the most fascinating and disturbing implications of the cosmic horizon. The universe is erasing its own history. Every moment, evidence of the Big Bang is being pushed beyond the cosmic horizon, where it can never be recovered. Let me explain what I mean by this. Right now, we can see the cosmic microwave background. This is the afterglow of the Big Bang, radiation that was emitted about 380,000 years after the universe began. At that time, the universe was a hot, dense plasma, filled with electrons and protons and photons all bouncing around together. As the universe expanded and cooled, the electrons and protons combined to form neutral hydrogen atoms. This is called recombination, even though the electrons and protons had never been combined before. When recombination happened, the photons that had been bouncing around in the plasma suddenly had nothing to interact with. They could travel freely through space, and they've been traveling ever since. Today, about 13.8 billion years later, those photons are still traveling through space. They've been redshifted by the expansion of the universe, stretched from visible light to microwave radiation. But they're still there, carrying information about the state of the universe when they were emitted. By studying the cosmic microwave background, we can learn about the density and temperature of the early universe. We can see tiny fluctuations in temperature that represent the seeds of all the structure we see today, the galaxies and galaxy clusters and superclusters. We can measure the curvature of space, the amount of matter and dark energy in the universe, and dozens of other fundamental parameters. The cosmic microwave background is arguably the most important source of information we have about the early universe. But it won't last forever. As the universe continues to expand and accelerate, the cosmic microwave background will be redshifted more and more. It will shift from microwaves to radio waves to longer and longer wavelengths. Eventually, the wavelengths will become so long that the radiation becomes undetectable. The photons will still be there, but they'll be so diluted and so redshifted that no instrument could possibly detect them. The cosmic microwave background will effectively disappear, and when it does, we'll lose one of our most important windows into the early universe. Future civilizations, living billions or trillions of years from now, won't be able to see the cosmic microwave background. They won't be able to measure its temperature fluctuations or learn about the density of the early universe. They'll have to take our word for it, based on observations we made billions of years earlier, assuming, of course, that our records survive that long. And it's not just the cosmic microwave background. Distant galaxies are also being pushed beyond the horizon. These galaxies are important because they show us what the universe looked like in the past. When we look at a galaxy that's 10 billion light-years away, we're seeing it as it was 10 billion years ago. We're seeing a younger galaxy, with more gas, more star formation, a different structure. By studying galaxies at different distances, we can piece together the history of how galaxies form and evolve. But as these distant galaxies cross the cosmic horizon, we lose that information. We lose the ability to see what galaxies looked like in the early universe. Future astronomers won't have access to that data. They'll have to rely on observations made by earlier generations. Or they'll have to use theoretical models to extrapolate backward from the galaxies they can see. But those models will be less reliable because they won't be constrained by actual observations of early galaxies. In other words, the further into the future you go, the harder it becomes to understand the history of the universe. Not because we get less intelligent or less technologically advanced, but because the evidence itself has been pushed beyond the cosmic horizon where it can never be retrieved. This is what I mean when I say the universe is erasing its own history. It's not a metaphor, it's a literal description of what's happening. Evidence is disappearing, information is being lost, and future civilizations will have a harder time understanding the cosmos because of it. Let me paint you a picture of what astronomy might look like in the far future. Imagine you're an astronomer living 1 trillion years from now. The Milky Way and Andromeda have long since merged into a single elliptical galaxy. We'll call it Milkomeda, for the sake of convenience. You're living on a planet orbiting a star in Milkomeda, and you're trying to figure out the nature of the universe. You point your telescope at the sky, and you see stars. Lots of stars, hundreds of billions of them, all part of Milkomeda. But beyond Milkomeda, you see almost nothing. No distant galaxies, no galaxy clusters, no cosmic web. Just empty space, growing darker and emptier in all directions. You might conclude that Milkomeda is the entire universe, that there's nothing beyond your galaxy except empty space extending forever. You'd be wrong, of course. There are trillions of other galaxies out there, but they've all crossed the cosmic horizon. Their light can't reach you anymore. As far as you're concerned, they might as well not exist. Now, you might try to figure out if the universe is expanding. You'd look for redshifts in the spectra of distant objects. But the only objects you can see are in Milkomeda, and they're all gravitationally bound to each other. They're not receding because of cosmic expansion, so you'd measure their velocities and find that some are moving toward you and some are moving away, with no particular pattern. You'd conclude that the universe is static, not expanding. Again, you'd be wrong. The universe is still expanding, faster than ever. But all the evidence of that expansion has been pushed beyond the cosmic horizon. You'd try to look for the cosmic microwave background. You'd build sensitive radio telescopes, searching for the faint afterglow of the Big Bang, but you wouldn't find anything. The cosmic microwave background has been redshifted to such long wavelengths that it's completely undetectable. It's still there, in some technical sense, but it's been diluted to the point where it's indistinguishable from zero. Without the cosmic microwave background, without distant galaxies showing redshift, without any evidence of expansion, you'd have no way of knowing that the universe began in a hot, dense state. You'd have no way of knowing about the Big Bang. You might come up with alternative theories. Maybe the universe has always existed in its current state, unchanging and eternal. Maybe Milkomeda is the only galaxy, and it formed from some local collapse of gas and dust in an otherwise empty universe. These theories would be wrong, But how would you know? All the evidence that could prove them wrong has been erased. Now, you might get lucky. You might find old records, data collected by astronomers billions of years earlier, when the evidence was still accessible. If those records survived, if they were preserved and passed down through countless generations, you could learn about the expanding universe and the Big Bang. But that's a big if. Civilizations rise and fall. Records get lost or destroyed. Languages change, making old texts unreadable. Technology becomes obsolete, making old data formats inaccessible. It's entirely possible that future civilizations would have no surviving records from our era. They'd be starting from scratch, trying to understand the universe based only on what they can observe. And what they can observe would be severely limited by the cosmic horizon. This scenario is not science fiction. It's the actual future of the universe, based on our best understanding of cosmology. Unless something dramatic changes, unless dark energy behaves differently than we expect, this is what will happen. The universe will continue to expand and accelerate, pushing more and more evidence beyond the cosmic horizon until future civilizations are left with almost nothing to observe. It's a sobering thought. But it also highlights just how privileged we are. We live at a time when the universe is still revealing its secrets, when the evidence of the Big Bang is still accessible, when we can still see distant galaxies and measure the expansion of space. This won't last forever, but it's lasting now, and that's a gift we shouldn't take for granted. Let me tell you about one more aspect of the cosmic horizon that I find particularly fascinating. It has to do with causality, with cause and effect, with which events in the universe can influence which other events. In physics, we have a concept called the light cone. Imagine you're standing at a particular point in space, at a particular moment in time. Your light cone is the set of all events in the universe that you can possibly influence or be influenced by. Events inside your forward light cone are events you can influence. If you send a signal, or launch a spacecraft, or shine a light, it can eventually reach any event inside your forward light cone. Events inside your backward light cone are events that can influence you. Any signal or particle or light ray that reaches you must have originated from somewhere inside your backward light cone. Events outside your light cone, either past or future, are causally disconnected from you. They can't influence you, and you can't influence them. This is a fundamental principle in relativity. Nothing can travel faster than light, so causal influence can only propagate at light speed or slower. If an event is so far away that light couldn't have reached it from you, or couldn't have reached you from it, then you and that event are causally disconnected. Now, here's where the cosmic horizon comes in. Because space is expanding, the light cones get distorted in interesting ways. In a static universe, your forward light cone would keep growing indefinitely. Given enough time, you could eventually influence any event anywhere in the universe. But in an expanding universe, especially an accelerating one, this is no longer true. There are regions of space that are receding so fast that no signal you send can ever reach them. Even if you send a signal at the speed of light, the expansion of space will carry those regions away faster than your signal can catch up. These regions are outside your forward light cone. You can never influence them, no matter how long you wait or what technology you use. And these regions are precisely the regions beyond the cosmic horizon. The cosmic horizon marks the boundary of your forward light cone. Everything inside the horizon is potentially reachable. Everything outside is not. This has profound implications. It means that the cosmic horizon divides the universe into two fundamentally different types of regions. Regions we can potentially interact with, and regions we cannot. Events happening beyond the cosmic horizon might as well be happening in a different universe entirely. They can never affect us, and we can never affect them. There's no chain of cause and effect connecting us. This is a deeper kind of separation than just being far away. It's a fundamental causal disconnection built into the structure of space-time itself, and it raises deep questions about the nature of existence and reality. If we can never observe something, never interact with it, never be influenced by it in any way, in what sense does it exist? This is not a question science can easily answer. Science deals with observable phenomena, with things we can measure and test and verify. But by definition, anything beyond the cosmic horizon is unobservable. We can infer its existence based on our understanding of the laws of physics. We can extrapolate from what we see inside the horizon to what we think exists beyond it. But we can never directly verify those inferences. Some philosophers argue that this makes talk of regions beyond the cosmic horizon meaningless. If something can never be observed, even in principle, then statements about it are neither true nor false. They're simply not the kind of thing that can have a truth value. Others argue that the laws of physics don't stop at the horizon. Space continues beyond it, governed by the same equations that govern space within it. Those regions exist just as surely as the regions we can see. We just can't access them. This debate touches on fundamental questions about the relationship between existence and observation. Does something need to be observable to exist? Or can things exist that we can never observe? These are not easy questions, and I don't claim to have definitive answers. But they're worth thinking about, because they force us to confront the limits of scientific knowledge. The cosmic horizon is not just a physical boundary, it's also an epistemological boundary, a boundary between what we can know and what we cannot. Let me return to the question of dark energy, because it's central to understanding why the cosmic horizon exists. Dark energy is one of the deepest mysteries in modern physics. We know it exists because we can see its effects. The expansion of the universe is accelerating, and that acceleration requires some kind of energy source. We call that source dark energy, but the name is really just a placeholder. We don't know what dark energy actually is. We don't know where it comes from or why it has the properties it does. All we know is that it exists, it's spread throughout space, and it causes space to expand faster and faster. The simplest explanation for dark energy is that it's a property of space itself. This is sometimes called the vacuum energy or the cosmological constant. The idea is that empty space, even completely empty space, with no matter or radiation in it, has a certain amount of energy. And because space is expanding, creating more empty space, the total amount of dark energy is increasing. This causes the expansion to accelerate. But here's the puzzling thing. When physicists try to calculate how much vacuum energy there should be, based on quantum field theory, they get an answer that's wrong by about 120 orders of magnitude. That's not a typo. 120 orders of magnitude. The theoretical prediction is 10 to the power of 120 times larger than the observed value. This is arguably the worst prediction in the history of physics. It's such a huge discrepancy that it suggests we're fundamentally misunderstanding something about the nature of space and quantum fields. There have been many attempts to explain why the observed dark energy is so much smaller than the theoretical prediction. Maybe there's some mechanism that cancels out most of the vacuum energy, leaving only a tiny residue. Maybe our calculations are wrong in some subtle way. Maybe quantum field theory doesn't apply to the vacuum in the way we think it does. But none of these explanations are fully satisfactory. The dark energy problem remains one of the great unsolved mysteries in physics. And it's particularly frustrating because dark energy is so important for the cosmic horizon. It's dark energy that causes the expansion to accelerate. It's dark energy that pushes galaxies beyond the horizon. It's dark energy that will eventually leave us isolated in our local group, surrounded by empty space. If we understood dark energy better, we might understand the cosmic horizon better. We might be able to predict exactly how it will evolve in the future. We might even find ways to probe beyond it, though that seems unlikely given the fundamental constraints of causality. But right now, dark energy remains a mystery. We can measure its effects, we can describe how it behaves, but we can't explain why it exists or what it fundamentally is. This is humbling. We live in a universe dominated by dark energy. About 68% of the total energy in the universe is dark energy, yet we have almost no understanding of what it is. It's as if we're living in a house and we don't know what most of the house is made of. We can see the walls and the floors and the furniture, but 68% of the structure is made of some unknown material that we can only detect through its gravitational effects. This situation is unlikely to change anytime soon. Dark energy interacts with matter only through gravity. It doesn't emit light, it doesn't absorb light, it doesn't participate in any of the other fundamental forces. The only way we know it exists is by observing how it affects the expansion of the universe. This makes it incredibly difficult to study. We can't bring it into a laboratory and examine it. We can't collide it with other particles to see what happens. All we can do is observe its effects on cosmological scales and try to infer its properties. It's a difficult way to do science, but it's the only option we have. And despite the difficulties, we've made progress. We've measured the amount of dark energy in the universe with increasing precision. We've constrained its equation of state, the relationship between its pressure and its density. We've tested whether it changes over time or remains constant. These are all important pieces of the puzzle, but we're still far from understanding what dark energy actually is. And until we do, our understanding of the cosmic horizon will remain incomplete. Now, let me take you on a thought experiment. Suppose you could somehow travel faster than light. Suppose you had a spacecraft that could violate the cosmic speed limit and cover vast distances in the blink of an eye. Could you use such a spacecraft to cross the cosmic horizon? Could you travel to a galaxy that's beyond the horizon and observe it directly? The answer is more complicated than you might think. First, let's be clear. As far as we know, faster-than-light travel is impossible. Special relativity says that nothing with mass can accelerate to the speed of light, let alone beyond it. As you accelerate, your mass increases, and it would take infinite energy to reach light speed. So faster than light, travel seems to be ruled out by the laws of physics. But let's set aside that objection for a moment and imagine that you somehow found a way to do it. You built a spacecraft that can travel at, say, 10 times the speed of light. You point it toward a galaxy that's beyond the cosmic horizon and hit the accelerator. What happens? Well, even at 10 times the speed of light, you'd still have a problem. The space between you and that galaxy is expanding faster than you can cross it. Remember, the cosmic horizon is defined as the distance beyond which space is expanding faster than light can travel through it. If you're traveling at 10 times the speed of light, the horizon is further away than it would be for light. But there are still regions beyond that extended horizon where space is expanding faster than you can travel. You could increase your speed to 100 times the speed of light, or 1,000 times, or 1,000,000 times. But no matter how fast you go, there's always a horizon beyond which space is expanding faster than you can travel. You can never catch up to a galaxy that's receding faster than you can move. It's like the treadmill analogy I used earlier. No matter how fast you run, if the treadmill is moving faster, you're not going to make any progress. The expansion of space is the treadmill, and it has no speed limit. Space can expand at any rate, arbitrarily fast, without violating any laws of physics. So even faster than light, travel wouldn't let you cross the cosmic horizon. Not unless you could travel infinitely fast, arriving at your destination instantaneously. But that's not really travel, that's teleportation. And teleportation, as far as we know, is also impossible. There's actually a concept in general relativity called a wormhole that might, in theory, allow something like faster-than-light travel. A wormhole is a shortcut through space-time, a tunnel connecting two distant points. If you could create a wormhole, you might be able to step through it and emerge at a distant location, having traveled a very short distance through the wormhole, even though you covered a huge distance through normal space. This wouldn't violate special relativity because you wouldn't actually be moving faster than light, you'd just be taking a shortcut. But there are several problems with this idea. First, we don't know if wormholes can actually exist. The equations of general relativity allow for them mathematically, but that doesn't mean nature actually creates them. Second, even if wormholes can exist, they would probably require exotic matter with negative energy density to keep them open, and we've never observed any such matter. Third, and most importantly for our purposes, creating a wormhole that connects us to a galaxy beyond the cosmic horizon would itself require sending something to that galaxy to set up the other end of the wormhole. And if the galaxy is beyond the horizon, we can't send anything there. So wormholes don't help us cross the cosmic horizon either. The cosmic horizon appears to be an absolute boundary, uncrossable by any means we can currently imagine. This doesn't mean it's impossible to cross it. Maybe there's some aspect of physics we don't understand yet, some new phenomenon or principle that would allow it. But based on our current understanding, the cosmic horizon is as uncrossable as the event horizon of a black hole. It's a fundamental feature of the universe we live in. Let me shift gears and talk about something that might seem unrelated at first, but actually connects to the cosmic horizon in a profound way: the arrow of time. We perceive time as having a direction. The past is different from the future. Events unfold in a particular order. Eggs can break, but they don't spontaneously unbreak. Ice melts, but water doesn't spontaneously freeze into ice cubes. We remember the past, but not the future. This asymmetry between past and future is called the arrow of time, and it's one of the deepest puzzles in physics. The fundamental laws of physics, at least at the microscopic level, don't have an arrow of time built into them. Newton's laws work equally well if you run time backward. The same is true for the equations of quantum mechanics and even general relativity. If you filmed fundamental particles interacting and then played the film backward, you couldn't tell the difference. The backward version would look just as physical as the forward version. Yet on the macroscopic level, time clearly has a direction. We age, we don't get younger. Buildings crumble. They don't spontaneously assemble themselves. The universe is expanding, not contracting. So where does the arrow of time come from? The standard answer has to do with entropy, a measure of disorder or randomness. The second law of thermodynamics says that entropy always increases over time in a closed system. Things tend to go from ordered states to disordered states. A clean room becomes messy, not the other way around. A hot cup of coffee cools down to room temperature. It doesn't spontaneously heat up. This increase in entropy gives time its direction. We can tell past from future by looking at which direction entropy is increasing. But this raises a question. If entropy always increases, the early universe must have had very low entropy. It must have started in a highly ordered state. And indeed, that's what we observe. The early universe was incredibly smooth and uniform, with only tiny density fluctuations. That's a state of low entropy. Over time, those fluctuations grew into the complex structures we see today: stars, galaxies, galaxy clusters. And with each step, entropy increased. Now, here's where the cosmic horizon comes in. As the universe expands and accelerates, as galaxies cross the cosmic horizon, we're moving toward a state of higher entropy. The far future of the universe, where our local group is surrounded by empty space, is a state of higher entropy than the present. And the ultimate future, the heat death of the universe, where everything has decayed and radiated away, is the highest entropy state of all. So the cosmic horizon is part of the arrow of time. It's part of the inexorable march toward higher entropy, toward a universe that's more spread out, more dilute, more disordered. We can't reverse this process. We can't bring back the galaxies that have crossed the horizon. We can't reverse the expansion and return to the hot, dense state of the early universe. Time has a direction, and that direction leads us toward the cosmic horizon and beyond. This connection between the cosmic horizon and the arrow of time is profound. It tells us that the boundaries of the observable universe are not just spatial boundaries, they're also temporal boundaries, markers of the universe's evolution from low entropy to high entropy, from order to disorder, from concentration to dilution. The cosmic horizon is where the arrow of time points. Now I want to talk about one more fascinating aspect of the cosmic horizon that connects to an idea you might have heard of, called the holographic principle. This is going to sound strange, but bear with me. Some physicists have proposed that all the information about what happens inside a region of space can be encoded on the boundary of that region. Like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. The holographic principle suggests that the universe might work the same way. That everything happening in three-dimensional space can be described by information encoded on a two-dimensional boundary. For the cosmic horizon, this has bizarre implications. If the holographic principle is correct, then everything that happens inside the cosmic horizon, all the galaxies and stars and planets, all the history and evolution and complexity, all of it can be encoded on the two-dimensional surface of the horizon itself. The horizon would be like a cosmic hard drive, storing all the information about everything within it. And as the horizon changes, as galaxies cross it and disappear from view, that information gets erased. It's a strange and speculative idea, and it's far from proven. But it's taken seriously by many theoretical physicists because it connects to deep ideas about quantum mechanics and gravity. The holographic principle emerged from studying black holes. Physicists realized that the amount of information that can be stored in a black hole is proportional to the area of its event horizon, not to its volume. This was surprising. You'd expect that the amount of information would depend on the volume, on how much three-dimensional space is inside the black hole, but it doesn't. It depends on the two-dimensional surface area of the horizon. This suggested that maybe all regions of space work this way. Maybe the maximum amount of information that can be stored in any region is proportional to the area of its boundary, not its volume. Applied to the cosmic horizon, this would mean that there's a finite amount of information that can exist within the observable universe. Not because the observable universe is infinite or finite in size, but because the horizon has a finite area. And as the universe expands and the horizon grows, the maximum amount of information increases. But as galaxies cross the horizon, information is lost. The information about those galaxies, about their stars and planets, and everything that happened there, gets erased from the cosmic hard drive. It's a thought-provoking idea, though I should emphasize that it's speculative. We don't have direct evidence that the holographic principle applies to the universe as a whole. But it's an active area of research, and it shows how the cosmic horizon connects to some of the deepest questions in theoretical physics. Let me also address a question you might be wondering about. If the universe is expanding, what is it expanding into? This is one of the most common questions people ask about cosmology, and it's based on a very natural intuition. When we think of something expanding, we usually think of it expanding into something else. A balloon expands into the air around it. A city expands into the countryside surrounding it. So it's natural to ask what space itself is expanding into. But the question is based on a misunderstanding of what we mean by the expansion of space. Space isn't expanding into anything. It's just getting bigger. The distance between distant galaxies is increasing, but they're not moving into some pre-existing void. The space itself is being created as the universe expands. This is hard to visualize because we're used to thinking of space as a stage where things happen, a fixed background against which objects move. But in general relativity, space is a dynamic, evolving entity. It can curve, it can ripple, it can expand, and when space expands, it doesn't need to expand into anything else. It just expands. To make this more concrete, think about the surface of a balloon again. Imagine you draw dots on the balloon to represent galaxies. As you inflate the balloon, the dots move apart. The surface of the balloon is getting larger. Now, the balloon is expanding into the air inside it. But we're not talking about the three-dimensional balloon. We're talking about the two-dimensional surface. From the perspective of a two-dimensional being living on the surface, who can only move along the surface and can't perceive the third dimension, the surface is the entire universe. And that universe is expanding, getting larger, even though from the two-dimensional being's perspective, there's nothing to expand into. The expansion is intrinsic to the surface itself. Our universe might work the same way. We live in three-dimensional space that's embedded in some higher dimensional structure, or maybe not. Maybe our three-dimensional space is all there is, and it's just getting larger intrinsically, without expanding into anything. The mathematics of general relativity doesn't require space to expand into anything. The expansion is a property of space itself, not a motion through some background. This is one of those ideas that's easier to accept mathematically than to visualize. Our brains are wired to think of space as a fixed container, but the universe doesn't have to conform to our intuitions. It is the way it is, regardless of how easy or hard it is for us to visualize. Let me tell you about one more implication of the cosmic horizon that touches on the nature of scientific progress. Throughout history, as we've developed better and better instruments, we've been able to see farther and farther into space. Galileo's telescope in 1609 revealed the moons of Jupiter and the phases of Venus. Better telescopes in the following centuries revealed nebulae that turned out to be distant galaxies. The Hubble Space Telescope, launched in 1990, revealed galaxies billions of light-years away. The James Webb Space Telescope, launched in 2021, is seeing even farther, detecting galaxies that formed just a few 100 million years after the Big Bang. This progression has been ongoing for 400 years. Each generation builds better instruments and sees deeper into space. It's natural to assume that this progression will continue indefinitely, that we'll keep building better telescopes and keep seeing farther and farther. But the cosmic horizon puts a limit on this. There's a maximum distance we can possibly see, no matter how good our telescopes become. We're already approaching that limit. The most distant galaxies we can see are close to the cosmic horizon. There might be a few more we can detect with better instruments, galaxies that are even closer to the horizon, but we're not going to increase the observable universe by a factor of 10 or 100. We're close to seeing as far as it's possible to see. This is a new situation in the history of science. For 400 years, we've been in a regime where better instruments meant seeing farther, but we're entering a regime where better instruments mean seeing farther, but only slightly farther. Eventually, we'll hit a wall. We'll have telescopes that can see everything there is to see within the observable universe. And then what? Science doesn't end, of course. There will still be plenty to discover. We can study the galaxies we can already see in more detail. We can look for planets around other stars. we can search for signs of life. We can investigate dark matter and dark energy. We can explore the early universe through the cosmic microwave background. There's no shortage of scientific questions to answer. But the era of exponential expansion in the size of the observable universe is coming to an end. We're in the final chapters of that story. This is bittersweet. On one hand, it's a kind of loss. The thrill of discovery, the sense that there's always something farther to see, has been a driving force in astronomy for centuries. On the other hand, it's a kind of completion. We're approaching a comprehensive view of the observable universe. We're mapping the full extent of what can be seen. Future generations will refine our understanding, will make more detailed observations, will answer questions we can't yet answer. But they won't fundamentally expand the boundaries of the observable universe. Those boundaries are set by the cosmic horizon, and we're already close to mapping them. In a way, we're living in the golden age of cosmological discovery, the age when humans first pieced together the full story of the observable universe, first mapped its extent, first understood its history, first grasped its ultimate fate. It's a privilege to be alive during this era. Let me also talk about what the cosmic horizon means for the search for extraterrestrial intelligence. For decades, scientists have been searching for signs of intelligent life elsewhere in the universe. We've listened for radio signals, looked for laser pulses, searched for signs of advanced civilizations altering their stars or galaxies. So far, we've found nothing. The universe appears silent. This is called the Fermi paradox, after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the universe is so vast, with so many stars and planets, why haven't we found any evidence of other civilizations? There are many possible explanations. Maybe intelligent life is extremely rare. Maybe civilizations destroy themselves before they become detectable. Maybe they're out there, but we're not looking in the right way. Or maybe they're beyond the cosmic horizon. If there are civilizations in galaxies beyond our cosmic horizon, we will never detect them. Their radio signals, if they're sending any, will never reach us. The light from their stars, including any artificial alterations they might make, will never reach us. They're completely cut off from us by the expansion of space. For all practical purposes, they might as well not exist. This is sobering. It means that even if the universe is teeming with intelligent life, we might only ever find a tiny fraction of it, the civilizations within our cosmic horizon. And as time passes and more galaxies cross the horizon, the number of potentially contactable civilizations decreases. We're in a shrinking pool of possible cosmic neighbors. Of course, even within the cosmic horizon, space is unimaginably vast. The observable universe contains 2 trillion galaxies. If even a tiny fraction of them harbor intelligent life, there could be billions or trillions of civilizations out there. But the cosmic horizon ensures that some civilizations, perhaps infinitely many if the universe is infinite, will forever remain unknown to us. They might be sending signals, might be building megastructures, might be doing all sorts of interesting things, but we'll never know. The cosmic horizon has cut us off from them as surely as if they existed in a different universe entirely. I want to return one more time to the personal, human significance of all this. The cosmic horizon is a scientific concept, sure. It emerges from general relativity and cosmology, from equations and observations and theoretical physics. But it's also something more. It's a reminder that we live in a universe with limits. That there are boundaries to what we can know, what we can explore, what we can experience. This can feel limiting, even oppressive. We're curious creatures. We want to explore, to discover, to push beyond every boundary. And the cosmic horizon tells us that no matter how far we push, There will always be a boundary we can't cross. But I don't think this should make us feel trapped or limited. Instead, it should make us appreciate what we have. The observable universe is vast beyond comprehension. It contains more stars than there are grains of sand on all the beaches on Earth. It contains more galaxies than there are people who have ever lived. It spans distances so large that light takes billions of years to cross them. Even if we're confined to the observable universe, even if we can never cross the cosmic horizon, we have more than enough to explore, more than enough to discover, more than enough to keep humanity busy for millions or billions of years. And here's something else to consider. The cosmic horizon, for all its absoluteness, for all its finality, is not a static thing. It's changing, evolving, responding to the expansion of the universe. In the early universe, the cosmic horizon was much smaller. As the universe expanded, the horizon grew, allowing us to see more and more. In the future, as the expansion accelerates, the horizon will shrink in terms of the number of galaxies it contains, but it will still be there, still defining the boundary of the observable universe. The cosmic horizon is part of the dynamic, evolving nature of the cosmos. It's a reminder that the universe is not a static stage. It's an unfolding story, a cosmic drama that's been playing out for 13.8 billion years and will continue for trillions of years into the future. And we're part of that story. We're not just passive observers, we're active participants, thinking and feeling beings who can contemplate the cosmic horizon, who can understand what it means, who can appreciate its significance. That's remarkable. In a universe where most regions are empty space, where most matter is dark and inert, where most of history is quiet and uneventful, we exist. We live on a planet where life arose, where consciousness emerged, where intelligence developed to the point where we can understand the fundamental nature of reality. The cosmic horizon doesn't diminish that. If anything, it enhances it. Because knowing about the cosmic horizon, understanding what it means, grasping its implications, that's an achievement. It's a testament to human curiosity, ingenuity, and perseverance. We've only been doing serious science for a few hundred years. We've only had telescopes for 4 centuries. We've only understood that the universe is expanding for about a century. And yet, in that brief span of time, we've figured out the fundamental nature of the cosmos. We've mapped the observable universe. We've understood its history, from the Big Bang to the present. We've predicted its future, including the role of the cosmic horizon. That's extraordinary. And it's a gift we can pass on to future generations. The knowledge we've gained, the understanding we've achieved, these things will endure. Long after we're gone, long after our civilization has transformed into something unrecognizable, the insights we've gained about the cosmic horizon will remain valid. They're truths about the universe, truths that don't depend on who's observing them or when. The cosmic horizon existed long before we understood it, and it will continue to exist long after we're gone. But we had the privilege of discovering it, of being the generation that first understood this fundamental feature of the cosmos. That's not nothing. That's something to be proud of. Let me conclude by bringing all of this back to a very human scale. What does the cosmic horizon mean for you, personally? What difference does it make in your life that there are galaxies beyond the edge of the observable universe? In one sense, it makes no difference at all. Those galaxies are so far away, so completely inaccessible, that they have absolutely no impact on your daily existence. You'll never see them, never visit them, never be affected by anything that happens there. For all practical purposes, they don't exist. But in another sense, knowing about the cosmic horizon changes everything. It gives you a perspective on your place in the universe. It reminds you that you're part of something vastly larger than yourself. Something so large that even our most powerful telescopes can only see a tiny fraction of it. It reminds you that the universe is not static and unchanging. It's dynamic, evolving, constantly transforming itself. Galaxies are being born and dying, stars are forming and exploding, space itself is expanding and accelerating. And through all of this, you're here. A conscious being, able to contemplate the cosmic horizon, able to understand the expansion of the universe, able to appreciate the profound strangeness of existence. That's remarkable. In a universe where most regions are empty space, you're in a region where matter has organized itself into stars and planets. In a universe where most matter is dark and inert, you're made of atoms that were forged in the hearts of dying stars. In a universe where most of history is quiet and unchanging, you exist in an era when stars are shining and galaxies are evolving. And you have the privilege of understanding this, of knowing about the cosmic horizon and dark energy and the Big Bang, of being able to trace the history of the universe from its beginning to its likely end. That knowledge doesn't make your problems disappear. It doesn't solve the challenges you face in your daily life, but it provides context. It reminds you that you're part of an ongoing cosmic story that began 13.8 billion years ago and will continue for trillions of years into the future. The cosmic horizon is a wall at the edge of everything, but it's not a wall that should make you feel trapped or limited. It's a wall that should make you appreciate how much there is to explore within the observable universe. How many stars to study, how many planets to discover, how many mysteries to solve. The universe may have boundaries, but those boundaries are so far away, so unimaginably distant, that they might as well not exist. What matters is here, in this galaxy, in this solar system, on this planet. Where you are right now, reading these words, thinking about the cosmic horizon, contemplating your place in the vast tapestry of existence. That's the real gift. Not the ability to cross the cosmic horizon, but the ability to understand that it exists, to marvel at it, to appreciate it, and to recognize that even with all its boundaries and limits, the universe is more beautiful and mysterious than we ever imagined. Thank you for spending this time with me tonight, exploring one of the most profound and beautiful concepts in all of cosmology. The cosmic horizon may be a wall at the edge of everything, but understanding it brings us closer to understanding the universe itself. And that understanding, incomplete and imperfect as it may be, is one of humanity's greatest achievements. If you enjoyed this journey to the edge of the observable universe, please take a moment to like this video and subscribe to the channel. It helps us continue creating content that explores the mysteries of the cosmos. And the next time you look up at the night sky, remember that you're seeing only a tiny fraction of what's out there. Beyond the stars you can see, beyond the galaxies visible in our most powerful telescopes, beyond the cosmic microwave background itself, there's a horizon, a boundary where the expansion of space finally overcomes the speed of light, a wall at the edge of everything, beyond which lie galaxies we'll never see, worlds we'll never know, and mysteries we can only imagine. But even with that horizon, even with those limits, the universe remains vast beyond comprehension. And we are privileged to live in a time when we can still see it, still study it, still marvel at its beauty and complexity. Good night, and sleep well under the stars, knowing that you live in a universe with boundaries, but also with wonders beyond counting.